Hello everyone, it's Mr. Pope from Wilmington Grammar School for Boys, and today we're going to be looking at quadratics. Okay, so this should be a fairly familiar bit of maths for you. I just want to finalise everything off so that we're all on the same page, and moving forward, quadratics is something that we spot, we like solving, and it's usually the technique we use when we're at the end of a problem and it boils down to a quadratic, or when something has a non-linear relationship. Usually you can factor down things into linear terms and quadratic terms and cubic terms and so on. Or, as we'll see later, what I call quids, quadratics in disguise. Essentially the really useful tool, algebraic tool to have in your skill set. And a lot of problems are quadratic ones, because essentially we live in a three-dimensional world, but a lot of problems, when you think about them, can just be broken down to 2 dimensions, and quadratics deals with two-dimensional movement quite well. Okay, so what is a quadratic? So I'm going to define a quadratic as a function. In terms of x and y, I mean, y and x could be anything, but you could have y equals some constant a times x squared plus a different constant b times x plus a constant c, where a, b and c all belong to the set of real numbers. Okay, any function that looks like that is a quadratic. So say, for example, I've got z equals 2d squared plus root 3d minus 7, then we would say that z is a function of d and z is a quadratic in d, or it's a quadratic of d. Quadratic equations, yeah, essentially they're going to be of this form. So the question is, what would we do with them? Well, let's suppose, and what happens quite often, we're asked to solve when ax squared plus bx plus c equals to 0. Now you're probably thinking, why 0? Well, if we let it be a number term, let's say d, then I can minus d from both sides, so this becomes c minus d, and we can just call this constant k, or just a new c, it's still a constant. And then similarly, if I had, I don't know, let's say that's still plus c, let's say I had some dx plus e, which is a linear term, and I subtract it to the other side, I've had ax squared plus b minus d lots of x plus c minus e. And then by same argument, this is still a quadratic in x. Even if you got to x squared terms, then you're still going to be left with a quadratic. So what do we do? I mean, obviously, if it's not a polynomial, we can't play this trick. But if we're dealing with polynomials, it might be a good start to figure out how we can deal with this. So there's various techniques. Okay, and the first one I'm going to be looking at is when we complete the square. Okay, and there's various techniques of doing this, and what we're going to do is, if I've got a constant in front like that, then I'll take that a out and make it x squared plus b over a, because I have to divide everything in the brackets by a to get x plus c over a, and this still equals to 0. Okay, next what do we do? Well, when you're completing the square, what we need to do is we're going to have brackets x brackets squared, and then whatever this term is, the coefficient of x, we halve it. So b over a halved becomes plus b over 2 of a, because b over a times a half will become b times 1, which is b, over a times 2, which is 2a. That should be pretty elementary. And then the next step is we always subtract. And then whatever this term is, squared. So b squared is on the top, and on the bottom 2a all squared, or 2 squared is 4, and a squared is a squared. And then don't forget this c over a term. And to get it over a common denominator, I want it to be 4a squared on the bottom. And it's already got an a there, so I need to times the top by 4a as well. So you can have 4ac on the top. Okay, next up. Well, if I redistribute everything out, I'm going to have a lots of x plus b over 2a squared plus, and now I've got a 4ac term on the top minus a b squared, and this is all over 4a squared, but it's been times by a, so it's going to be 4a. And this equals to 0. And now, technically, I have got it in completed square form. What's useful about that is this bracket will tell us that when x equals minus b over 2a, this is the x coordinate of the vertex, and this value here, the end term, is the y value of the vertex. And we'll go through examples of what that means. But I haven't actually solved it yet. I haven't got x equal to anything yet. But we say getting to this point as we've completed the square. So if I was to carry on, I'm going to subtract the orange term to the right hand side. So I've got a lots of x plus b over 2a squared equals minus 4ac minus b squared over 4a. And if I redistribute this out and have minus 4ac minus b squared, so that becomes plus b squared. So this will actually become b squared minus 4ac. If I divide both sides by a, then I'll get x plus b over 2a all squared equals b squared minus 4ac over 4a squared. And now if I square root both sides, I'll get x plus b over 2a equals the positive or negative square root of b squared minus 4ac. And this is all over the square root of 4a squared. Well, the square root of 4 is 2, and the square root of a squared is a. Now, if I subtract b over 2a to the right-hand side, because they both have the same denominator, this is going to be x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. So, this form of solving the quadratic is being done by taking the general quadratic and completing the square. But actually, this form is also known as the quadratic formula. Okay, so this quadratic formula people use a lot. You're supposed to, be able to use this at GCSE, and for A level, you're not going to be given a formula sheet with it on. You're just expected to have memorised it. It's not particularly difficult to memorise. Yeah, I don't mind it. It's okay. It's a bit formulaic, but it will get the job done. I usually complete the square because it tells you, important stuff like the x coordinate of the vertex and the y coordinate and so on and so on. But it's a matter of style at this point. Let's make this pink or green. There you go. Okay. How do I get that? Okay, so one technique of solving is by completing the square. Another technique is the quadratic formula. There is a third technique, okay, and this is by factorising. Okay, so if you've got ax squared plus bx plus c equals to 0, this technique will only work if b squared minus 4ac is itself a number squared. Okay, and you don't have to do this check. but I technically would do it because b squared minus 4ac is actually in the quadratic formula. So by doing that, best case, you can prove that it can be factorised and it's fairly quick. And worst case, you've proven it can't be factorised, so you don't waste any time and you can just go straight to the quadratic formula. So it's a bit of a win-win. It just takes that whole guesswork out of it and just gives you like a routine of what you can just get on with. So, factorising, really simple. The technique is to think of two numbers that add to b, the coefficient in the middle, but multiply to a times c. And then what you need to do is once you've found those two numbers, split up the coefficient of x and then factorise as if they were linear pairs. So it's probably best with an example like this. So let's take 3x squared minus 8x minus 3. Okay, so can you factorise this? Well, is b squared minus 4ac a square number? Well, b squared, that's minus 8 squared, minus 4 lots of a, which is 3, lots of c, which is minus 3. Minus 8 squared is 64. 4 times 3 is 12. Times by 3 again is 36. And minus minus makes a plus, that's plus 36. 64 and 36 makes 100, and that is 10 squared. So yes, this can be factorised. So the next trick, the next part of the thing, is we've got to think of two numbers that add to the middle coefficient, which is minus 8, and multiply to the product of the outside two. So 3 times minus 3 is minus 9. What two numbers add to minus 8 but multiply to minus 9? I believe that's minus 9 and positive 1. So now look what I'm going to do. I'm going to take these two numbers, minus 9 and positive 1, and that's how many x I have. Because minus 8x plus x is still, minus 9x plus x is still minus 8x. So I'm going to rewrite the rest. So 3x squared, that stuff, minus 3. This is still okay. And then what I'm going to do is I'm going to draw an imaginary line and I'm going to factorise a pair at once. So how would I factorise 3x squared minus 9x? Well, they both have a 3 in common and they both have an x in common. So this is going to be x minus 3. Now if I copy this bracket over to here, x minus 3, how many x minus 3s does it take to get an x minus 3? Well, that's plus one of them. And now we're ready to go. So this means I've got 3x plus 1, which are the coefficients of the things in front of the brackets. And then the other bracket, as you've probably guessed, is this repeated x minus 3. Why is this particularly useful? Because I'm asked to solve 0 equals 3x squared minus 8x minus 3. That's the same as this bracket equals this. And essentially, why is factorising so powerful? Because if I have two numbers and I multiply them together and I tell you that the result is 0, that means either one of them is 0 or the other one's 0 or potentially both are 0. So let's work out the potentials of what they could be. So if this bracket equals 0, then I've got 3x plus 1 is 0. Well, that's easy. 3x equals minus 1 if I subtract 1 from both sides. So x will equal minus a third. And if I look at the other case where x minus 3 could be 0, then x is just going to equal 3. Okay, so that's nice. Why is that useful? What does that mean? Well, it means if I was to plot y equals 3x squared minus 8x minus 3, then if I was to draw my coordinate axis, I know that it crosses the x-axis at 3 and minus a third, because on the x-axis that's when y equals 0, and I know the values for x for which y is 0. And I also know, funnily enough, where it crosses the y-axis, because the number term at the end, minus 3, tells us it's down here at minus 3. Because when x is 0, I've got 3 lots of 0 squared minus 8 lots of 0, I just get y equals minus 3. And by the way, if there's no constant term, they're just all x's, i.e. 3x squared minus 8x minus 3, like that, like this, and that just means it crosses through the origin when x is 0. So you don't have to panic, it's still doable. So, generally speaking, y equals ax squared plus stuff, when a is positive, is going to give a u-shape, and this is called a u-shaped parabola. And then when y equals some ax squared and the rest of it when a is negative, then this is going to be an n-shaped parabola. Okay, now these arcs, like this arc here, is like how a ball would fly through the air if you threw it. Okay, it's like a loop. Okay, a ball would be thrown through the air. It was what's called, it would have a parabolic flight. And when we do mechanics, we'll actually see why quadratics are the shape of objects being thrown, projectiles. And if you're wondering, well, if a equals 0, the final case, then clearly this isn't a quadratic, not a quadratic, because it needs that x squared term to really define it. Okay, so what else can I infer? Well, I can infer that because the number in front of x squared, the coefficient 3, is positive, it's going to be a u-shaped parabola that goes through these 3 points, and it's going to look like that. Oops, daisy. Okay, and to work out the x-coordinate and the y-coordinate of the vertex, and the vertex is this thing down here, that's the vertex. So I could just type in the numbers. It's going to be minus b over 2a, so minus 8 over 2 lots of 3. Well, the minus make positive, so it's 8 over 6, that's 4/3. And the y value is 4ac, so 4 lots of 3 lots of minus 3 minus 8 squared all over 4 times 3. Okay, 4 times 3 times 3 is minus 36, minus 8 squared is 64, because that makes positive, so that's minus 100 over 4 times 3, so that's minus 100 over 12. You can divide by 4 top and bottom to get minus 25 over 3. And if you're wondering, we could have also completed the square on this. So what would that look like? Well, we'd have had y equals, let's take 3 out as a factor, x squared minus 8/3 x minus 1. Okay, now I usually stick with fractions, and the reason for that is because if we go back to, where was it, here, when we subtracted that number squared, this squared gave this term, then it's easier to square fractions. You square the top, square the bottom, whereas if I've got a decimal number, it's not immediately obvious. I mean, if I asked you to square 2.25, you'd probably be like, what is that? Whereas to me, 2.25 is 9/4, so if I square that, that's 81 over 16. And yeah, that is a lot easier to work out. Okay, so next up, y equals 3 lots of x brackets squared minus half of 8/3 is 4/3, and then I always subtract. It doesn't matter what this sign is in here, and this sign always matches this sign. 4 over 3 squared is just 16 over 9, and that is a terrible 6. And then I minus 1, which is 9 over 9. Get it over a common denominator, save you some work. So y will equal 3 lots of the bracket x minus 4/3 squared, and then minus 16 minus 9 is minus 25, and it would be over 9, but because you times them by 3, it's going to be over 3. And now look, does this agree? When this bracket equals 0, what minus 4/3 is 0? Well, that's 4/3, so that agrees. And then similarly, what did I say over here? Yeah, no, that's it. And then similarly, this number here, minus 25 over 3, does agree with over there. Okay, couple of other interesting points. Parabolas are symmetrical. They have a line of symmetry, vertical line of symmetry at x equals the vertex point. So in this case, x equals 4/3. Okay. You may be asked to describe a geometric transformation of what's going on here. And it's very simple. There's a couple. In the x direction, it's moving right 4/3, and that's it. In the y direction, it's being stretched by a factor of 3, and then it's being translated downwards by minus 25/3. Hoping you can see that. We're going to be talking about transformations of graphs next Monday. Well, probably the Monday after that, actually. I think we're doing equations and inequalities next. But essentially, if you are asked that, then just be aware that all parabolas are just the same. They've just been transformed. They're a family of functions. There are many different ways of solving quadratics. Completing the square is one of them. And solving the quadratic formula is another one, and factorising and solving that way is another valid one as well. Given a quadratic, you should be able to sketch them. You should be able to write down points of value, or notable points, i.e. where the quadratic crosses the x and y values, if at all. It's definitely going to cross the y value, the y-axis, sorry. The x value it might not. We'll talk about that in a second. And you need to be able to distinguish where the vertex is. Okay, so I've got a couple of questions. It should be fairly easy. If you want to pause the video and give it a go, just have a drink. Okay, first question. So, where a and b are constants, I've got to prove that this is the case. Find the value of a and b. Okay. So what this wants me to do is complete the square, because I've got a square there and a corrective term. That's fine. So I'm going to have x brackets squared. I halve the minus 8, which is minus 4. Then I always take away this term here, which is 16 squared. And then I bring down the minus 29. So what am I going to have? I'm going to have x minus 4 all squared. And minus 16 minus 29, I believe that's minus 45. So the value of a is minus 4, and the value of b is minus 45. Pretty easy. Hence or otherwise, show that the roots of that are c plus or minus d root 5, where c and d are integers to be found. Okay, so what it's asking me to do is, using completed the square form, so x minus 4 all squared minus 45, I'm going to set that equal to 0 and now solve. So I'm going to add 45 to both sides, so 45 equals x minus 4 all squared. I'm going to square root both sides, so x minus 4 equals the plus or minus root of 45. And now we've done a bit of surds. Root 45, you should be able to jump to 3 root 5, because 45 is 9 times 5 and root 9 is 3. And this equals x minus 4, and then I'm going to add 4 to both sides, so 4 plus or minus 3 root 5 is the answer. This means there's two solutions, either x equals 4 plus 3 root 5 or x equals 4 minus 3 root 5. That's what that means. So it looks like c, the number term, is 4, and d, the coefficient of root 5, is 3. That's my final answer for that. Yeah, not bad. Pretty early past paper question for AS. Okay, try another one. Pause the video, give it a go. Okay, express x squared plus 10x plus 19 in that form. Oh, we've got to complete the square again. So this is going to be x plus half of 10 is 5 squared, minus the 5 squared is 25, bring the 19 down. So this is going to be x plus 5 all squared, minus 25 plus 9 is minus 6. So for part I, that's done. Part II, write down the coordinates of the vertex of the minimum point of the curve with that equation. Well, what must x be? So the bracket is 0, that's minus 5, and then this term here minus 6. So it's got a minimum point at x is minus 5 and y is minus 6. That's the whole point of completing the square. You've just found the minimum point fairly easily. Maybe when it comes to algebraic proof, when we do that later, I'll show you why it's called completing the square. But for the point of just, keeping the videos to about an hour or shorter, I'm going to, do it another time. Write down the equation of the line of symmetry of that curve. Well, as I said before up here, it's just x equals the x coordinate of the minimum, the vertex, because it's got, vertical symmetry. So that's just going to be x equals to negative 5. Then part 4, describe geometrically the transformation that maps y equals x squared onto the graph. Okay, so what does y equals x squared look like? It looks like this. Why does it look like that? Because when y is 0, x is 0, and if we try and do the quadratic formula, the only points we're going to get out is just 0, so it must be looking like that. And now let's have a look at what we're saying is going on here. So it's got a minimum at minus 5 and y is minus 6, so it's down there, and it crosses the y-axis at 19 up here. So it's going to do something like that. So in actual fact, because there is no there's no multiplication going on at the beginning, then what's gone on is it's gone left 5 and down 6. So describe geometrically the transformation that maps the graph y equals x squared. Okay, so it's a translation of column vector minus 5 minus 6. And remember, it's a column vector xy alphabetically. So translation of minus 5 minus 6 means it's gone to the left 5 and down 6. Part B, determine the coordinates of the intersection points of the line y equals x plus 11 and that. Okay, so we're going to solve simultaneously. So let x plus 11 equal to x squared plus 10x plus 19. So we subtract that over, so we're going to get x squared, 10x minus x is going to be plus 9x, and 19 minus 11 is plus 8. Well, I think this factorises, does it not? Because I can think of two numbers that add to the middle, which is 9, and multiply to 1 times 8, which is 8. And those two numbers are 1 and 8. And in the special case where there's a 1 in front of the x squared, we can actually jump to x plus 1 times by x plus 8. Okay, you could have done it the long way. I mean, let's convince ourselves that that would be the same thing. So let's put this to the side. So how would that look? Well, this would be x squared plus 1x plus 8x plus 8. Draw a line. X squared plus x becomes x times x plus 1. Put the x plus 1 here. This is clearly 8 lots of that. So then you have x plus 8, which is x plus 8. And then x plus 1 there. Yeah, works out. So in the special case of when the coefficient of x squared, i.e. a, the a term, is just 1, then once you've done the whole adds to the middle, multiplies to the product of the outside, a and c, then you can just read it off. So, but it's not over yet, because it says determine the coordinates of the points of intersection. Well, we have to solve this. So when x plus 1 is 0, then that clearly means x is minus 1. And when x plus 8 is 0, we're going to get x equals minus 8. But it wants coordinate points, and every coordinate in the two-dimensional space, the plane, which is the Cartesian coordinate axis, there's going to be a y value. And all we have to do is add 11 to our x values to get y, because it lies on the line and the curve. I mean, we could have done this to it to get y, but I just fancy adding 11, that just seems easier. So minus 1 add 11 is 10, minus 8 add 11 is 3. So there are the 2 points. X is minus 1, y is 10, and x is minus 8, y is 3. Okay, yeah, just being like really comfortable with completing the square, solving quadratics, being able to sketch them, describing geometrically what's going on, that kind of thing. It's all good skills. Right, now, a more useful property. The discriminant. What is the discriminant? Why is it useful? The discriminant is the b squared minus 4ac part of the quadratic formula. Okay, and it's called the discriminant because it literally discriminates what kind of quadratic it is. So I'm going to do all the different cases. So when a is positive and b squared minus 4ac is positive, well, let's have a little two-way table. So along the top, I've got a is positive, a is negative. I need three of these. Right. So if b squared minus 4ac is positive, then if I was to draw a graph of x and y, that means if the discriminant is positive and a is greater than 0, then that means our quadratic cuts and it has two real solutions. Two real solutions. And they're distinct. Okay, that means they're different. Okay, so two real distinct solutions. Now, if a is less than 0 and b squared minus 4ac is still positive, then what's going on is a very similar thing, but this time you've got an n-shaped parabola and there's still two real distinct and what's called roots or solutions. Solutions, roots, it's fine. Okay, now what about when b squared minus 4ac equals to 0? Well, let's draw our coordinate axes. When it's greater than 0, then we're going to have a quadratic that just touches one and only point. So it has one repeated real root. And it's a U-shaped parabola because a is positive. And then you're probably guessing what's going to happen here. If a is negative, then what we're going to have is we're going to have a negative parabola. Doesn't matter where it is translated left to the right, but the important feature is it only touches the x-axis once, and there's going to be one repeated root. Okay, and now what happens when b squared minus 4ac is negative? So there are three cases: positive, so when it's positive, when it's 0, or when it's negative. Now when it's negative, if a is positive, then that means your quadratic is floating above the x-axis. So we say there's no real roots, and actually what's happening is they're complex, which means we're going to have to start using stuff like I. They're going to be of the form, that was an example, but they're going to be of the form a plus bi. Okay, they're going to be complex. You know, that doesn't mean they don't exist, but there's a real part and imaginary part. That's just, you know, terminology. They do exist. They're just complex. But in terms of A-level maths, you can stop there and say there's no real solutions. There may be complex ones, but typically A-level maths only does real analysis, whereas further maths, we look at the complex case. What happens when a is less than 0? Well, that's going to be a vertically opposite thing. So there's going to be no real solutions there. And if solutions do exist there, they're going to be complex. And they're also going to be of the form of a plus ib, or bi. Bi. Whatever, I can put ib, it's fine, it's interchangeable. Okay, so a lot to do with this chapter is to be able to identify keywords. So if it's the case where the discriminant is positive, it has two real distinct roots. Doesn't matter what a is, that's the key thing. If the discriminant is positive, there's two distinct real roots. If the discriminant is 0, then there's one repeated root, i.e. there's only one solution to the quadratic, and it looks like that. And then finally, I've had orange. And then finally, if the discriminant is negative, that means your graph is floating away from the x-axis, either above or below, depending if it's a U-shape or N-shape, and there are no real solutions. So you can almost stop your analysis there, and you only have to consider complex solutions. And depending on the question, they might only want real solutions, so you can stop. Okay, a couple of side notes. If b squared minus 4ac is greater than 0, then it might factorise or it might not. So you might have to use the quadratic formula, you might have to complete the square. It's not that obvious. But when b squared minus 4ac is 0, notice that 0 is 0 squared. So this will 100% factorise, and it will always factorise to ax minus b squared. And the point of where it bounces is always x is going to be b over a. Okay, what I'm trying to say is there's always a repeated bracket, and it will always factorise. It will always factorise to a repeated bracket. It just will. And then b squared minus 4ac is less than 0. Well, this will never factorise. Well, it will never factorise with real numbers anyway. I mean, you could probably fiddle around with it and force it to be factorised with complex numbers, but then technically we don't really do that, mathematicians. I mean, you can, it's not against the rules or anything, but generally speaking, you'd never write something as a product of complex factors. But totally fine, it's up to you. So the discriminant is really useful. You can determine what's going on, you can determine the shape, the position of a quadratic, and you can determine, more importantly, how many solutions there are. So yeah, it's really good. I suggest you make a mental note of that. So now I'm going to do some questions. And typically you need to be really good with quadratic inequalities to solve these. But let's have a look. Pause the video, have a go for yourself. I'll go through them in a second. Okay, quadratic equation blur, where p is a constant, has equal roots. Determine the possible values of p. Right, so that means 4x squared plus 16 minus p, lots of x, plus 13 minus p, set it equal to 0, is our quadratic. And 4 is our A, 16 minus p is our B, and 13 minus p is our C. And if p has equal repeated roots, that means b squared minus 4ac equals to 0. So what does that mean? It means b, which is 16 minus p in this case, squared, minus 4 lots of a, which is 4, lots of c, which is 13 minus p, that equals to 0. Okay, so 16 minus p squared. If you expand out double brackets, 16 times 16 is 256. You're going to get 2 lots of 16 times minus p, which is minus 32p, and you're going to get a plus a p squared. Then you're going to have minus 4 times 13, and 4 13s are 52. So 52 times 4 again is 208, so it's going to be minus 208. And then minus 4 times minus p is going to be plus 16p, and that equals to 0. Interesting. Well, let's tidy this up. I've got a p squared, done, so that's done. I've got a minus 32p and a plus 16p, so that's minus 16p, so that's done, that's done. Then 256 minus 208, that's just 48, isn't it? So that's plus 48 equals to 0. Okay, right. So does this factorise? Well, after a while you kind of get a grasp of whether they do or not. And can you think of two numbers that add to minus 16 and multiply to 48? Well, I think it's minus 12 and minus 4. So this becomes p minus 12 times by p minus 4. So the two values of p are p is 12 and p is 4. And what we need to do is have a look at the question and see if there's any values of p we can't find. So determine the possible values of p. Yes, I've done that, 12 and 4. Solve the equation for each of the p values found in A. Okay, now if they have equal roots, and this means that this equation can be set up as brackets, brackets, something squared equals to 0. So let's do this. So first one, we're going to have 4x squared plus, and let's do the case when p equals 12. 16 minus 12 is 4x, plus 13, but then this is 12. 13 minus 12 becomes plus 1. And if you think about it long and hard, I think that's going to be 2x plus 1 all squared. Because 2x times 2x is going to be the 4x squared. 2x times 1, double that is the 4x, and 1 times 1 is 1. That equals 0. So that means 2x plus 1 is 0 repeated, so then x equals minus a half. Repeated root. And now if p is 4, so when p equals 4, we're going to have 4x squared plus 16 minus 4, which is plus 12x, plus 13, but then we're going to minus 4, so that becomes plus 9. Whoa, when you get good at spotting these, I think that's going to be 2x plus 3, isn't it? Because 2x times 2x is going to be a 4x squared if we expand double brackets. 2x times 3 and then double that gives the 12x. Yep, 3 times 3 is 9. Bosh. So this means 2x plus 3 is going to equal to 0 because square rooting 0 is still 0. Minus 3 from both sides divided by 2. X equals minus 3 halves. So the only cases where this quadratic has equal roots is when x is minus a half and x is minus 3 halves for p is 12 and p is 4 respectively. Okay, how about you try this one, the quadratic equation, this, pause it, give it a go. You might have to use inequalities, I'll talk about them in a second. Okay. Quadratic equation, that thing, where k is a constant, where k does not equal minus 2, has two distinct real roots. Right, so that means the discriminant b squared minus 4ac is positive, it's greater than 0. Because that's what this key phrase, two distinct real roots, means. Show clearly that k is trapped between this. Right, okay, so what is b squared? This is b. So if I square it, minus minus becomes a plus. So I'm going to have 5k plus 7 all squared, minus 4 lots of a, and a is this thing. So that's 4 lots of 3 lots of k plus 2. And c is this thing, the constant term, which is 3k plus 1. It's not adding, that's timesing, you silly boy. It's 4ac. That is greater than 0. Okay, lot to digest here. So let's do this in stages. 4 times 3 is 12. So I can get rid of this, make that 12, and then, okay, let's deal with this. Now what I'm going to do is I'm going to pick out terms. So if I look at the k squared terms, I'm going to have 5k times 5k, which is 25, but then I'm going to minus 12k times 3k, 12 times k times the 3k is where the k squared is going to be there, so it's going to be minus 36k squared. So this is actually going to be minus 9. Is that right? Oh, you silly boy, it's minus 11, isn't it? Minus 11k squared. Yes. Okay. Now let's consider the k terms. Well, 5k times 7 is 35. Double that is going to be 70k. Minus, and then the k terms here, we're going to have a 3k times 2, which is 6, plus a 1, which is 7. 12 times 7 is 84k. So 70k minus 84k, I believe, is minus 14k. Good. And then the number terms, I'm going to have 7 squared is 49, minus 12 times 2 times 1 is 24. 49 minus 24, I believe, is 25. Okay, right. So how do you solve a quadratic like this? Well, your Casio FX 991E, the Casio FX 991EX calculator from Woolworths, not Woolworths, lol, from WH Smith's. usually about 20, 25, 30 pounds will solve this for you. Otherwise, we're going to cover this in inequalities, but what I would do is I'd make the amount of k squareds positive. So if I times by -1, that's going to be 11k squared plus 14k minus 25 is less than 0. And the reason why we flip the inequality, notice how it's gone from greater than to less than, is because let's suppose I have -1 is less than 2. That's true. If I multiply both sides by -1, this becomes 1 and -2. And now the inequality doesn't hold anymore. But now, if I flip it, it does. So whenever you multiply or divide by a negative number, you've got to flip the inequality. Right, okay, now this is just a quadratic. So what we're going to do is we're going to ignore we're going to sketch it. So try sketching 11k squared plus 14k minus 25 equals to 0. Okay. Wow, that's not nice. Okay, we need to find the solutions of it. So I'm going to jump to the quadratic formula. So k equals minus b, which is minus 14, plus or minus the square root of 14 squared, which is 196, minus 4 lots of a, which is 11, lots of c, which is minus 25, and this is all over 2 lots of a, which is 22. Oh boy. Right, so 190, let's look at the discriminant. 4 times, okay, so it's going to be a plus because a minus and a minus. 4 25s are 100, so that's 1100. If I add the two together, that's 1296. I know 1600, the square root of that is 40. This ends in a 6. Could it be 36 squared? Because anything ending in... Okay, fine, let's check that. So 36 times 30... You'd use a calculator at this point, you know, don't bother with me. So 6 times 6 is 36, 6 times 3 is 18, plus the 1. 3 times 6 is 18, 3 times 3 is 9, plus the 1 is 10, 6, 1, 9. Aha! So, in actual fact, k is minus 14 plus or minus the square root of 1296, which is 36, all over 22. So what's that going to be? Minus 14 plus 36. Well, that's 36 minus 14, which is 22. So k looks like it's going to be 1. Or minus 14 minus 36 is minus 50 over 22, which is minus 25 over 11. So that means if we've got a quadratic that's looking like this, it's a U-shaped parabola that crosses at 1 and minus 25 over 11. It's going to go like that. And we want the section that's lower than 0, remember? Well, that's going to be this section, which is between 1 and minus 25 over 11. So that means k is going to be less than 1, but greater than minus 25 over 11. And is that the right answer? Yes, bosh. Yeah, very tricky question. Yeah, taken from a Madass paper. Check out the Madass website. I just think his questions... It's Dr. Triffer Madass who wrote all of them. I can't get enough. He's just like... The difficulty of questions, if you can tackle all of them, you're set up. They're so demanding, intricate, fiddly. Yeah, just... He's obviously spent a lot of time over a very long period of time developing these questions. I did create lots of videos on the past paper, or on the papers that he made, and it's just great fun to do. Yeah. Anyway, so last question. So if f of x is that thing, show clearly that the equation f of x equals 9 has 2 distinct real roots for all values of k. Okay, so if 4x squared plus 12kx equals to 9, because all I'm doing is setting f of x equal to 9, then that means 4x squared plus 12kx minus 9 equals to 0. So what is the discriminant here? The discriminant is b squared, or b is 12k, so that's 144k squared, because square the 12 and square the k is going to be 100k, minus 4 lots of the a, which is 4, times c, which is minus 9. Well, 144k squared, we'll leave it as it is. Minus minus becomes a plus. 4 times 4 is 16. 16 times, pardon me, is 144. 16 times 144. And this clearly factorises to 144 times k squared plus 1. Well, if you know anything about numbers, 144 is definitely positive, and k squared plus 1 is also positive as well, because if I square a number, the lowest it can be is 0. So the smallest this thing can be is 1. And clearly any number that's 1 or bigger is positive. So a positive times a positive is a positive. Therefore, we've just shown b squared minus 4ac, the discriminant, is positive. Therefore, it has 2 distinct roots for all real k values. The only way it wouldn't is if k was a complex number. So yeah, technically not right. It's not all values of k. K could be a complex number, but never mind. We'll forgive them. Okay, hence find the solutions of f of x equals 9, given the answer in the form of that. Right. Okay, so we've already got the discriminant. So it's going to be minus b, which is minus 12k, plus or minus the square root of the discriminant, or the square root of this thing. Square root of 144 is 12, and then it's square root of k squared plus 1, and then this is all over, and then this is all over 2 lots of a, which is 8. So there's common denominatory things going on here. So 12 over 8 you can divide by 4 to get 3 over 2. So x is going to equal minus 3 over 2k plus or minus 3 over 2 lots of the square root of k squared plus 1. So in actual fact, it looks like p equals minus 3 over 2. And if you have a minus in front of the plus minus thing, that just becomes a minus plus, and essentially it's positive or negative, so don't have to worry about that. So yeah, interesting question. Another mad-ass question. You can probably tell from the style of fonts. Okay, right, there's 2 more bits left. Hang in there, guys. I know it's almost an hour, but we've got to bang this. So, quadratics in disguise. Right, Edexcel and other exam boards love to do this. They kind of get absolute, they get so excited when they manage to write a question and there's a quadratic in disguise in there, and they feel so great for tripping up some students. What do I mean by a quadratic in disguise? Well, let's say I've got something like this. Let's say 4 to the x minus 2 to the x plus 2 equals to 0. And you're like, what on earth are you on about? That's not a quadratic. It's not even a polynomial. You've got some weird things to the powers. This doesn't make sense. How is this a quadratic in disguise? And you have to be vigilant for these things. Whenever you spot there's like a 2 or 3 term equation going on in there, equaling to 0, or you can make it so it equals to 0, you've got to think to yourself, is there a substitution that can turn this into a quadratic? And the trick to this is to realise that 4 to the x is the same as 2 squared to the x, and that's the same as 2 to the x all squared. And now, if you let a equal 2 to the x, so a squared is that, then the first term becomes a squared, the next term becomes minus a, and the plus 2 stays the same. Oh look, now we have a quadratic in a squared minus a plus 2. And this is really easy. This is going to be a minus 2 times by a plus 1 to factorise. So a equals 2 or a equals minus 1. But we haven't actually solved it because a was 2 to the x. That means 2 to the x is 2, or 2 to the x equals negative 1. Well, you can't raise 2 to the power of a real number and it be a negative 1, so that hasn't got a solution. So the only solution here is 2 to the x equals 2, which means that x equals 1. Well look, doesn't it? 4 to the 1 is 4, minus 2 to the 1 is 2, plus 2, does that equal to 0? Don't think it does it? Where have I made a boo-boo? Oh, that's where I made a boo-boo. This doesn't actually factorise. Okay, this should have been a minus. That's a minus, that's a minus. Okay, yeah, and that factorises. Yeah, fine, sorry. So ignore all that. This is supposed to be a minus. Bad typo. I was doing it in my head. I knew what I meant. Anyway, so it's like that. If I had 4 to the x minus 2 to the x minus 2 equals to 0, it would be like that. By the way, what would happen if it wasn't that? Let's say I had to solve 4 to the x minus 2 to the x plus 2 equals to 0. And that would still, same way, minus a squared minus a plus 2 equals to 0. Could I complete the square on this thing? Yes, I'd have a minus a half squared minus a quarter plus 2 equals to 0, which means a minus a half squared minus a quarter plus 2 is plus 7 quarters. And then a minus a half squared would equal to negative 7 quarters. And then we're in trouble because if we square root 2, we would get the square root of a negative number, which isn't real. But you know what, for giggles, let's just go for it. So if I square root both sides, a minus a half equals plus or minus root 7i over 2. And if I add a half to both sides, a equals 1 plus or minus root 7i over 2. So in actual fact, if there was a plus 2 there, there would be solutions, but they'd be complex ones. So that's how you'd solve it in that case. If it was just for A-level maths, you would stop at this point and you would say there's no real solutions. Okay, now I can't list every single type of quadratic in disguise that there are, because essentially they're out there depending how creative you want to be. They appear everywhere. They appear in vectors, they appear in calculus, geometry, algebra, pretty much any kind of topic I can think of or subtopic in that, you know, whether it's parametric equations, differential equations, even in decision maths, you know, they happen all the time. So I'm not going to list off where they happen. All I can say is you're going to have to be on alert. You've got to be ready for them. And one question you've got to ask yourself is, can an equation that you've seen before be converted into a quadratic and be dealt with? Okay, so I'm just going to go through a couple, and I think if memory serves, they're logarithm questions. So if you want to go back and refresh yourself with log rules, not this one, but the other ones are, yeah. So first one, pause it, give yourself a go, and I'll try and convince you why this is a quadratic in disguise. Okay, so why is this a quadratic in disguise? Because if x doesn't equal to 0, I can actually multiply by x everywhere on both sides. So if I multiply this side by x, it becomes x squared plus 9. And if I multiply this side by x, it becomes 15 over 2x. Now if I multiply 15 over 2, subtract 15 over 2 from both sides, I actually get this quadratic to solve. There's multiple ways of doing this. You could multiply by 2, see if it factorises. You could quadratic formula. I'm going to do completing the square again for giggles. So x minus 15 over 4 squared minus the thing squared. 15 squared is 225 over 4 squared is 16 plus 9. 9 16s are 144 over 16. And then this is going to be x minus 15 over 4 squared equals, if I add the 225 and then minus 144, I've got to add 56 to this. What's 56? Add 25. That's 81, isn't it? So that's 81 over 16. That's great, because then if I square root both sides, then this is going to be plus or minus square root of 81, which is 9, over square root of 16, which is 4. And then x is going to be add the 15 over 2, so it's 15 over 4, plus or minus 9 over 4, which means x equals 15 plus 9, which is 24 over 4, so it could be 6, or 15 minus 9 is 6, isn't it? So 6 over 4 is 3 over 2. So x can either be 6 or 3 over 2. The final thing we have to do is, because we've solved this equation, we should always check to see if our answers if we sub them back in, makes sense. So if x is 6, does 6 plus 9 over 6 equal 15 over 2? Well, 9 over 6 is 3 over 2, and 6 is 12 over 2. And 12 over 2 plus 3 over 2 does equal 15 over 2, so that's valid. So x equals 6 is muy bueno. When x is 3 over 2, what have we got here? So we've got 3 over 2 plus 9 divided by 3 over 2 is the same as 9 times by 2/3, isn't it? Because you're dividing by fractions. 9 times 2/3, well, 2/3 of 9 is 6, so it's 6 plus 3 halves again. And I'll look, by symmetry, that's going to be the same as that. So yes, it does work. So both of those are valid solutions. If they weren't valid solutions, we called them extraneous solutions, because they solved algebraically the problem, but from an extra equation that we magicked up. It doesn't actually solve the original problem. So if these didn't work, they'd be called extraneous solutions. Okay. Right. So what we got here? Okay, solve the following logarithmic equation. You might want to look at the change of base log if you want a hint for this one. Okay, here you go. So, first of all, I noticed the logarithms of different bases. So the first thing we need to do is get them into the same base. I'm going to remember the log rule of log b of a becomes log x of a over log x of b. Yes, and I can check that's right with an example. I don't know, let's say I've got log of 25 to the 625, and I know this is 2 because 25 squared is 625, and if I want to get it as the base of 5, if I have that over that, then 5 to the power 4 is 625, so that's 4 over, and that's squared, 4 over 2 is 2, yep, that works. Okay, fine. So, right, so this is going to be log base 4 of x minus, now I take the 2 up in a power, so that's going to be 16, get rid of the 2. So this is going to be log base 4 of the argument, which is 16, over log base 4 of the old base, which is x. And now this equals to 1. Why have I done it this way? Because log 4 of 16 is really easy to do. 4 to the power of what is 16? This is just 2. So the equation becomes log base 4 of x minus 2 over log base 4 of x equals to 1. And then the beauty of it is, if you let log base 4 of x equal, I don't know, a or b, doesn't matter, then the equation becomes a minus 2 over a equals 1. If I times everything by a, I get a squared minus 2 equals a, and if I minus the a to that side, I get a squared minus a minus 2 is 0. That is a muy bueno quadratic we can solve. So a little bit of picking there, but it's now a quadratic. It was a quadratic in disguise. This should be easy now. It should be a minus 2 times by a plus 1, I believe. Is that right? Yeah. So then a equals 2 or a equals negative 1. Same deal, we're going to have log base 4 of x equals to 2, or log base 4 of x equals to minus 1. So the way we read this is 4 to the power of 2 is x for that one. So 4 squared, so that means x is 16. And then for the other one, we've got 4 to the power minus 1 is x. So it looks like x could be 4 to the minus 1, which is just 1/4. We should always check to see, extraneous solutions, that kind of thing. So let's have a look. For x equals 16, what is log base 4 of 16 minus 2 lots of log base 16 4? Does that equal 1? Well, log base 4 of 16, 4 to the what is 16, that's 2, minus 2 lots of, and then 16 to the what is 4, well, that's a half, isn't it? So 2 minus 2 halves is 2 minus 1, that does equal 1, tick boom. Then when x is a quarter, and we're allowed to take logs of real numbers, that's fine. Well, anything that's non-negative. Well, you can't take log of 0. Okay, fine. Anything that's positive. Positive reals. So log base 4 of a quarter minus 2 lots of log base a quarter 4. Okay, does that equal 1? Well, 4 to the what is a quarter, that's minus 1, because 4 to the minus 1 is a quarter, minus 2 lots of, and then a quarter to the what power is 4, well that's minus 1 there, so we're going to have minus 1, minus 2 lots of minus 1 is plus 2, and minus 1 plus 2 does equal 1, that's the desired result. Hippie, hippie, hooray. Cool. So yes, x equals 16 and x equals a quarter are valid solutions to this. Okay. Last loggy one for you. It's a real stinker. Yeah, pause it, give it a go. Right, okay, so what do you need to do here? Well, first of all, you do the opposite of what the original one was, i.e. you take the powers down as factors. So to the power 7 means that's 7 log 4 of x, and you can take that 2 down as a factor like so. And then if we use the substitution, let log 4 of x equal to a or b, it doesn't matter, then this whole thing becomes 2 minus 7a all over 7 minus 2a plus a squared equals to 0. Oh, so actually, yeah, this isn't going to be a quadratic, but we might have to use quadratics later on. Okay, so if I multiply by 7 minus 2a both sides, I'll get 2 minus 7a plus a squared, lots of 7 minus 2a equals to 0. Okay. Right, let's expand this and see what happens. So I've got 7 times a squared, so that's 7a squared there, and I've got a squared times minus 2, so I'm going to have minus 2a cubed, and I have minus 7a there, and I have a 2. If I get this in descending powers of a, I multiply everything by minus 1 to get 2a cubed minus 7a squared plus a 7a minus 2 equals to 0. I almost want to collect up the a terms. There's the set. Okay, let's tidy this up. So we've actually got 2a cubed minus 2 here, and then minus, and then we've got 7a squared minus 7a here. Why is it minus 7a? Because minus times a minus is a minus. Okay, generally speaking, factorising cubics is quite difficult, but with a bit of practice you can kind of have a play with it, see what happens, and I think this will work out. I've got a funny feeling it will. Anyway, let's try and factorise as we go. So 2a cubed minus 2 is 2 lots of a cubed minus 1, and 7a squared minus 7a is 7a lots of a minus 1. Oh, I'm so close. Okay, so I'm going to be a bit sneaky here. Difference of squares, difference of cubes, difference to the power 4s. Okay, this is a bit sneaky. You're not taught this at school. I'll show it to you. So if I've got a squared minus b squared, that is a minus b times by a plus b. Now if I've got a cubed minus b cubed, that is a minus b times by a squared plus ab plus b squared. And then if I've got a to the 4 minus b to the 4, this is a minus b times by a to the 3 plus a squared b plus ab squared plus b cubed. And if I've got a to the 5, this is minus b to the 5, this is a minus b times by a to the 4 plus a cubed b plus a squared b squared plus ab cubed plus b to the 4. Can you spot a pattern? Can you see what's going on? They all have this a minus b term in front, and I'm going to abuse that, because if I let b equal to 1, then a cubed minus 1 is a minus 1 times by a squared plus ab. So that's going to be, a plus b squared, which is plus 1. So in actual fact, this, if I take this off as a side note over here, then what I've got is 2 lots of a minus 1 times by a squared plus a plus 1 minus 7a lots of a minus 1. Oh, lo and behold, they both have an a minus 1 as a factor. So if I take a minus 1 out as a factor, I'm going to have 2 lots of this thing, which is 2a squared. 2 times a is 2a, but then I have minus 7a lots of that, so it's going to be minus 5a. And then 2 times 1 is going to be a plus 2. Oh, happy days. Why is that great? Because I'm pretty sure this factorizes to... Let's see if we can do it intuitively. It's going to be a 2a and an a there. It's got to multiply to 2 at the end. So I'm pretty sure this is the 2 and this is the minus 1. Because 2a times minus 2 is minus 4. That's another minus 1, so that gives the minus 5. And minus 1 times minus 2 is positive 2. Oh, that's beautiful. Why is that beautiful? Because this is a is 1, or a equals a half, or a equals 2. And you all get quicker at spotting these solutions. And then what was the upshot of this? Well, a was log base 4 of x, isn't it? So we've got to solve log base 4 of x equals to 1, log base 4 of x of a half, and log base 4 of x equals 2. So 4 to the 1 is what? Well, that's 4. That's the solution. 4 to the half is x. Well, that's the square root of 4, which is 2. And 4 squared is x, which means x is 16. Okay, now to check these aren't extraneous, let's substitute these back in and see if we've got the right idea. So, right, where are we? Let's get rid of these. Okay, now, the only thing to be careful of is, are we going to be dividing by 0 here at any point in time? Well, if I take the 7 out there and the 2 out there, then log base 4 of 4 is 1. That's a half, that's 2. If I substitute any of those into there, 7 minus 2 lots of 1 is 5, so that one's okay. X equals 1, and then if that's a half, I've got 7 minus 2 lots of a half, which is 7 minus 1, so that's 6, so that's okay. And 7 minus 2 lots of 2 is 3, so that's okay. And then I can always substitute in real values in for x, that's totally fine. Positive values, that's totally fine, we haven't got anything silly. Real values, negatives can be fine. Can they? No, they can't, they have to be real positives. Okay, cool. So there it was. Okay, the final thing. This is the final thing. Modelling with quadratics. What is this about? What is modelling? Well, modelling is all about taking a real life situation or problem and then attempting to make a model, or to simplify it, using techniques known already. Then you solve the model and then you apply it back. Well, and then you apply the solutions, and then you kind of you will make adjustments to the model. Okay, a model is, well, it's just like what you know a model in real life. If I make a model of a paper airplane, it's clearly not a paper airplane, but I'm using the skills and resources I currently have to best represent what an actual airplane is. Now, I can go away and refine that. I could maybe like snip some bits off and make the wings pointier and more aerodynamic, or I could actually go away and, you know, make a plane, a remote controlled one maybe, and I can make better and better models, and there's this process of constantly evaluating a model and getting it better and better and better. the key point here, this is not just for quadratics, this is for all different types of topics, is the key point of a model is sometimes real life problems are too complicated to solve, or there's too many factors, or there's underlying distributions we have no idea how they work. And so we attempt as humans to break things down into easier problems that are fairly close, and then we solve the model's problem. We apply that solution back to the real world, and if it doesn't work, then we go, okay, what underlying assumptions did we get wrong, or do we need to introduce more assumptions to better enhance our model? And then we go away and solve the new problem with the new model, and it's a back and forth system. You can, unless you get it absolutely right first time, this process doesn't really have an end. You can keep refining models, and what it comes down to in terms of A-level maths undergraduate stuff is you've really got to understand the context of the question. You've got to look at the model, solve it, and then go, right, so what does that answer actually mean? You can create all these fancy equations, and you can invent new areas of maths and solve this problem that essentially you've stepped so many steps to the side in order to be able to play around with it. And then when you do solve it, what does that mean to the original problem? And modelling in general just means, on the one side, you have to be thinking, right, how do I solve this mathematically? And then on the other hand, you've got to be thinking, right, the question is a real life context. How would I communicate my answer and interpret it so that people are wanting to understand the results? So for example, if I wanted to interpret a linearized graph, and somebody said, well, what is this constant value here, this b value or whatever? Now I could say to them, for example, that it would be the slope. It would be the gradient of this linearized function, and that technically would be true. You've told them that it's a slope. It would be the gradient of this function. The problem is that person either isn't expecting that answer, or doesn't know what that answer means, or that's not really the answer they're looking for. What they might be asking for is for an interpretation of that in the context of the problem. For example, that slope might mean revenue per day. The person might want to know, okay, this slope means we're earning about $2,000 a day. Cool, okay. And if we change this, how will that affect it, and so on. Modelling is all about, you are given problems and you have to interpret them, move sideways. It's just more flexibility. I think with problem solving, you've got to be flexible and solve problems that are unfamiliar, and you've got to be flexible in one way. But I think with modelling, you have to be more of a flexible communicator. You've got to be able to go, okay, what's the bigger picture here? How do I communicate what I've just done? So really, modelling, there isn't any new topics to learn, for example. I mean, if you can do everything that we've done so far, you can recognise quadratics in disguise, you can deal with the discriminants, you know what a quadratic graph looks like, you can solve quadratic inequalities, you can complete the square, find turning points, find solutions to it, factorise it, know the quadratic formula. There are other esoteric things. There's great YouTube channels out there that do all kinds of fancy stuff with quadratics. One of my favourite things about quadratics, I only found out a couple of years ago, was that if I have the y equals x squared graph, there it is, that if I have an x value there, let's call it minus a, so let's call that a, and I have a b value there, b, and I draw a straight line between the two, then where it crosses the y-axis is the value a times b. So if this was minus 4 and this was 3, then this y value of the intercept would be 12. And I just think that really nice, interpretation of quadratics as multiplying is just... Anyway, there's so many things you can do with quadratics. I've rabbited on for an hour and 20 already. Please go out there and, Google, look it up. There's so many books, there's so many people who know stuff. Just go out there. I'm not going to exhaustively list out everything to do with quadratics. Just go look it up. Anyway, let's go through a couple of examples of modelling with quadratics, and we'll call it a day. So, same as always, I'm going to let you guys pause the video, give it a go yourself. And we'll go through it. So, here you go. A company makes a particular type of children's toy. So there's real life situation. The annual profit of the company is modelled by the equation P equals 100 minus 6.25 x minus 9 all squared, where P is the profit measured in thousands. Please be aware it's in thousands. And X is the selling price of the toy in pounds. A sketch of P against X is shown in figure 1. So there's clearly this maximum point there. So I'm guessing the first thing people will be looking for is what's that maximum profit. Okay, using the model, explain why £15 is not a sensible selling price. Well, let's have a look at this. If I do 15 minus 9, that's 6. 6 squared is 36, so I'm going to have 36 times by, and 6.25 is 6 1/4, which I believe is 25 over 4. And then the 4 and 36 will cancel, so that'll be a 9. 9 25s, I believe, are 225. So P becomes 100 minus 225, which is negative 125. What does that mean on a graph? Well, our model is, for all intents and purposes, a quadratic function. So that means 15 is over here somewhere, because we can tell where this maximum point is because it's in completed squared form, so that when x is 9. So 15 is over here such that the y value, if I was to trace it across, would be at minus 125. And that would be disastrous because a profit of minus £125,000, you'd lose, you essentially you're losing £125,000. The model is predicting you're losing £125,000 by doing that. Whether that's true or not, so there's various different things. It could be that the cost of raw materials. I don't know. The point is, this model has predicted it's not a particularly good idea. Maybe once you go over a certain point, the workers start wanting overtime based on hours, so it becomes more costly per unit after a certain point. Who knows? There's various reasons that you could make. But explain why £15 is not a sensible selling price for the toy, because when X is 15, because X is the selling price of the toy, then that would mean that you would lose £125,000 in profit, because P is the profit, and a loss of profit is the same as just losing money, and that's you don't want to lose money. That's kind of like the number one rule of business. You want to make money, as in not make as in fabricate, but make as in earn money. You sell goods or services at a profit, and therefore you have more money than after all the deductions. So, given the company makes an annual profit of more than 80,000, find, according to the model, the least possible selling price. Right, so 80,000. So that means when P is 80, because we're still dealing in thousands. So as long as the profit is greater than 80, so this is 100 minus 6.25, that's 25 over 4 again. Now you'd be allowed a calculator for this question. And the reason I'm doing it in fractions is I'm not going to, I'm not using a calculator. So if I minus 100 from both sides, it's minus 20. So that's minus 25 over 4, x minus 9 squared. If I times by minus 4, that's 80, and then that flips, 25. So minus 9 squared. And if I divide by 25, let's see, 80 is 16 fives, and that's 5. So x minus 9 all squared is less than 16 over 5. Okay. Right, so if I treat this as like a equal sign, so then x minus 9 equals plus or negative root of 16, which is 4 over the root of 5. And if I rationalise that, that means x minus 9 equals plus or minus 4 root 5 over 5. And if I add 9 to both sides, 9 fives are 45. So if I had a quadratic, which I do, then 45 plus 4 root 5 is going to be over here. That's 45 plus 4 root 5 over 5. And then 45 minus 4 root 5 is still positive, and it's over here. So 45 minus 4 root 5 over 5. It's going to be a U-shaped parabola like that. And I want where the parabola is less than 0. So the optimal selling price is between here and here. So the least is 45 minus 4 root 5 over 5. And because we're interpreting this for people, I am going to use a calculator for this. What is 45 minus 4, where's the root button on this? I always do this. Aha, there it is. Root 5 over 5, which is, okay, this appears to be about £7.21. But it's 7.2111 and so on. So really, the least possible needs to be £7.22. Because if it's less than £7.22, well, if it was £7.21, that's less than the 7.2111 and so on, so that's not making a profit, so it needs to be the next one up. Okay. The company wishes to maximise its profit. State according to the model the maximum possible annual profit. Well, the maximum possible annual profit is when x is 9, so this disappears, so it's £100,000. It's the selling price of the toy. Well, that's easy. That's just when x is 9, so it's £9. So according to this model, if the toy sells for £9, then I maximise the profits for £100,000. Cool. Okay. One more, and that's it. It's the last one. So pause the video, give it a go yourself if you want to have a go. Okay, a company started mining tin in Riverdale on the 1st of January 2019. A model to find the total mass of tin will be mined by the company Riverdale is given by that equation, where T is tons of total, T tons is the total mass of tin mined in the N years after the start of mining. Using this model, calculate the mass of tin that will be mined up to the 1st of January. Okay, so up to the 1st of January is when n is 1, right? It's up to 1 year after. Okay, so when n is 1, t is going to be 1,200 minus 3 lots of 1 minus 20, which is minus 19, squared. So 19 squared is, it's 19 squared. Is it 361? What is it, 19 times 19? Yeah, boy, and then times that by 3. So it's 1,200 minus 1,083. So it's going to be 117 minus, I'm using the calculator, sorry. Okay, so it looks like 117 tons. You have to put the unit because we're interpreting a real life thing. Deduce the maximum total mass of tin that could be mined. Well, the total maximum, okay, this is clearly an n squared graph. If I was to expand this, I would get minus 3n squared plus a bunch of stuff. Why would it be minus 3n squared? Because n times stuff, when you expand this, will be an n squared, because it's a squared bracket, and I'm timesing it by minus 3. Now, minus 3n squared, that is because it's a negative n squared graph, it's going to be an n-shaped parabola like that. And once it's in completed square form, this thing, if I let this bracket equals to 0, will tell me the n value for that maximum, and that's clearly 20. So to deduce the maximum total mass of tin, well, when n is 20, this disappears and it's going to be 1,200. Just to check, T tons is the total mass of tin. So it would be tons. 1,200 tons. Calculate the mass of tin that we mined in 2023. Okay. Interesting. Well, this it's a little okay. Here's my thought process. 2023. Oh no, that's fine. So 19 to 20. Okay, so what we need to do is we need to find the sum when n, because this is the total, right? So we do it. We do the 2023 year minus the 2022 year, right? Because when we sub n appropriate n value for 2022, that'll be the sum up to 2022. And when we do the n value for 2023 minus that, we'll get what was done just in that year. It's a little bit of a tricky one here. So what is the n value for 2023? Well, when n is, let's count it. If n is 1, we're at the start of 2020, right? Because it's the 1st of Jan. When n is 2, we're at the start of 2021. When n is 3, we're at the start of 2022. So when n is 4, we're at the start of 2023. So that's the lower one. So n is 5 is when we're at the start of 2024. So really we need to sub 5 into this. So 1,200 minus 3 lots of 5 minus 20 squared, and then minus 1,200 minus 3 lots of 4 minus 20 squared. Okay, the reason I've done this is because the 1,200s cancel. The minus changes to a 3 lots of 4 minus 20 squared minus a 5 lots of 20. Okay, yeah, because you've got minus 3 there, so 3 times minus, yep, and then minus 3, yes. So now we've actually got 3 lots of 4 minus 20 is 16 squared, minus 5 lots of 20 is 15 squared. 16 squared is 256, and 15 squared is 225. 256 minus 225 is 25 plus 6. Oh, it's 31 times 3, so 3 times 31, so it's 93 tons is the answer. State, given reasons, the limitation of the values of n. Well, okay. What are the limitations of it? Well, if for n being a large value, you would actually have negative mass of tin mined. And how would that make sense exactly? How can you have negative tin? I mean, okay, fine. Let's do it this way then. If I wanted this to be less than 0, so 1,200 minus 3n minus 20 squared. If I add that to that side, that's n minus 20 squared is greater than, divide by 3, so it's 400. Well, what's going to happen here? N minus 20, another way of looking at this is you go along 20 like that, and you're going to have a quadratic that bounces like this, and the line 400 is here. So I want to know what this value, let's say x is, past the 20, where that is the 400. So 20 squared is 400, so n minus 20, when does that equal 20? Well, that's when n is 40. So really it's give or take 20 from either side, so really I've drawn that poorly, that should have gone through there. So really, when n is greater than 40, this is going to be negative 10, which is just silly. You can't have that. Is that right? Let me double check. Yeah, no, that is right. When n is greater than 40, we're not going to worry about when n is less than 0 because that's backwards in time. That's a bit silly. But you could have 40 years in the future. That could be 2059. So apparently from 2059 onwards, you're going to have negative 10, and that just seems a bit silly. Okay, cool. Well, I hope you enjoyed that. As I said, there's no real hard and fast way of answering quadratic modelling questions, or just modelling questions in general. I think what you have to do, as I've said before, is you solve it and you think about the context of the question and how would you explain your answer to somebody who's not a maths expert and doesn't get things like quadratics, surds and all that stuff. They just want to know what your answer to their problem is. Just imagine that somebody's come to you knowing that you know a little bit about maths and they've said something like, oh, you're good at problems, you're good at maths, why don't you solve this for me? Here's the information, go and make a model and you'll just go away and solve it for me. And then as a mathematician, you've made a model, you've solved it, and then you've got some things to interpret, and then you now need to communicate back to the person with the problem what's going on. Okay, thanks very much guys. Toodaloo.